Good evening, everyone. Imagine with me a future where air travel is significantly cleaner, quieter, and even faster than today. NASA's new Aviation Horizons initiative is laying the foundation for a future of sustainable aviation. Through wind tunnel testing of aircraft, concepts, engines, and a renewed emphasis on flight testing, or X-planes. A future where green is king. New Aviation Horizons is all about supporting a green future for the planet, whether it be through the assessment of advanced alternative and biofuels in jet engines and their emissions into the atmosphere, or one of the many other key technologies that NASA is developing with industry and university partners across the nation. We're at the right place, at the right time, with the right technologies to enable a radical transformation of the air transportation system. From concept to reality, NASA's aeronautical innovators are preparing to put in the sky an array of X-planes, or experimental vehicles, each of which is targeting key technologies to enable dramatic reductions in fuel burn, noise, emissions, and even to enable high-speed flight. Some of these goals include a 50% reduction in fuel usage, greater than 50% reduction in carbon emissions, and aircraft so quiet that you can barely hear them outside the airport boundary. New Aviation Horizons is accelerating to a new horizon of aviation for the nation and for the world. The details of how we're going to get from here to there are laid out in President Obama's fiscal 17 budget request, a request that lays out a bold 10-year plan to design, build, and fly a series of experimental aircraft, or so-called X-planes. These are X-planes to enable a green future for the nation. X-planes are nothing new. They're a way to advance technologies and accelerate industry's acceptance of these technologies so they can be brought to market. In fact, many of the technologies that you and I enjoy on current aircraft that we fly on, perhaps that some of you flew on to come here, have been developed through NASA partnerships with industry. Through computational fluid dynamics, many of the engine technologies that you'll see here, as well as winglets, composite structures. A lot of these technologies came from NASA developments with industry partners. Now, NASA Innovation in X-planes goes way back to our predecessor organization, the National Advisory Committee for Aeronautics, or NACA, which worked with the US Air Force to develop the very first X-plane, the X-1 vehicle shown here. Looking forward, the future X-planes, one of the key candidates for these X-planes is a hybrid wing body concept, which gets away from the familiar tube and wing aircraft that we're all familiar with today, and the wing blends smoothly into the fuselage. Not only does this offer dramatic fuel burn reduction potential, but also is much quieter than current aircraft, as demonstrated by this simulation. Other key technologies that we're focusing on are long, slender wings supported by a brace, non-circular fuselage concepts that allow the aircraft to get some lift from the fuselage as well as from the wings, as well as engines that are partially embedded into the fuselage to improve performance. The truss brace wing concept shown here has been developed in partnership with the Boeing company. The bracing of the wing from below allows for a long, slender wing design that reduces drag and improves aerodynamic performance. Wind tunnel tests indicate a 5 to 10% fuel burn reduction from this technology. It also has a high wing mount to allow for the incorporation of large diameter, high bypass engines. The D8, or so-called double bubble concept, because it has a fuselage that's twice as wide as it is high, has been developed in partnership with MIT, Aurora Flight Sciences, and Pratt & Whitney. In addition to the double-wide fuselage, which provides a lifting characteristic, it also has engines mounted at the rear of the vehicle that ingest the boundary layer that flows over the vehicle itself. Boundary layer ingestion is important because it allows for improved performance of the vehicle as the engine ingests air that's already been slowed down by having flown over the vehicle itself. At NASA Glenn, we're currently in the process of testing an advanced fan with an industry partner to assess the benefits of BLI and to optimize the fan design for this configuration. We're also very excited about the single-aisle turboelectric aircraft concept, which is also called Stark ABL for short. Now, this aircraft looks fairly typical to the casual observer because it's a tube and wing with two engines under the wings. But note the tail cone thruster fan in the back, which also takes advantage of this BLI phenomenon. In addition, the power is routed from the main engines to that rear fan turboelectrically, another key innovation. System studies indicate a 15% fuel burn reduction benefit for this concept. NASA is also learning from small-scale demonstrations, such as the latest NASA X-plane, the X-57 Maxwell. This small electric aircraft allows us to learn about system integration, and we can apply those learnings to larger electric aircraft in the future, such as the N3X concept, where all power is distributed electrically across the rear of the aircraft, and BLI is leveraged fully. Now, all of these concepts are going to require advanced engines, and in particular, high power density, small, compact core, or the heart of the engine. At NASA Glenn, we're very proud of our heritage in propulsion technology, and as these core engines become smaller and more higher power, the temperatures go up to very high levels, causing challenges for material technology, as well as the size of the components becoming very small, challenging the manufacturing techniques. We're working with GE Aviation, Pratt & Whitney, and other partners on developing these core engine technologies. Now, so far I've shown you concepts that fly subsonically around Mach 0.8, or typical of today's airliners. But what if we could fly across the country in half the time that it takes today? That's the idea behind our supersonic X-plane concept, where the aircraft is designed in such a way that it produces smaller boomlets that are less objectionable to people on the ground. Now, flight research is a key component in aeronautics research, but it's only a part. There's a three-legged stool that we like to talk about in terms of research, the first leg being computational analysis capability. This is where researchers use sophisticated computer models and high-speed supercomputers to predict the flow over an aircraft or through an engine or over part of an aircraft. It's critically important that researchers can understand how an aircraft is going to perform through analysis, in particular when the concepts look much different than today, as in the D-8 aircraft or an open rotor, as shown here. The second leg of the research stool is experimental or wind tunnel testing. This is where researchers take a scale model of an aircraft or part of an aircraft, or an engine or part of an engine, and flow air over that in a wind tunnel and measure the data resulting from that. In this way, researchers can understand the performance of these concepts, look for areas of interest for further research, and then take the data and go back and improve the numerical methods that were used in the first place. You can then loop back and use those improved models to improve the designs in kind of an iterative loop. And the third leg of that research stool is, of course, to fly the concept and test it in flight. This is where all the learnings from the computational and wind tunnel testing are brought to bear in a flight asset, and you can really demonstrate that the benefits are measurable in a flight vehicle. Not only can you demonstrate the benefits, but you can also reduce the risk of bringing the concept to market for the industry. NASA Glenn Research Center here in Cleveland, Ohio, along with our partner centers, NASA Langley in Virginia, and Ames and Armstrong in California, are working together to realize the vision of new aviation horizons for NASA. And at Glenn, we're very proud of our heritage in propulsion, material research, turbomachinery, and many other areas. They're going to be key contributors toward this vision. To quote Dr. Jae-Won Shin, NASA's Associate Administrator for Aeronautics Research, "This is an exciting time for the entire NASA aeronautics team and for those who benefit from aviation, which is frankly everyone. With this 10-year plan to accelerate the transformation of aviation, the United States can maintain its status as the world's leader in aviation for many years to come." Thank you very much, and I'd like to thank all those who helped with compiling this video, as well as our many industry and university partners. Thank you very much.